So our next session is on fair workflows, and I welcome my co-chair, Anka Angela.
Good morning, everyone. Big welcome also from my side to this fourth day of Big Data from Space. I'm Anka Angela. I'm part of the digital innovation team of the European Space Agency in EOP, Earth Observation Programs. Okay, so let's get this session started. I'd like to invite our first speaker, Felix Kremer from Max Planck Institute of Biogeochemistry, who will talk to us about FAIRSEND, fair workflow for Sentinel-1 based deforestation detection. Felix, you have 15 minutes in total, so 10 plus 5. Thank you.
Okay, thank you. Yeah, good morning, everyone. I'm going to talk today about our project FAIRSEND, which is basically the task is bringing a science-evolved workflow into the cloud and making it fair. So we started with this forest change detection workflow we developed earlier, and now the idea is to make this findable, accessible, interoperable, and reproducible, so that everyone could go on a website and make it themselves for their area of interest, for their time frame of interest. And so to start, the workflow of the processing is as follows. We start with Sentinel-1 data. Currently, we use already pre-processed data on 20 by 20 meter. Then we apply a recurrence quantification analysis algorithm that I'm going to explain in a minute. And then we mask the forest areas, we do a threshold on significance, and then we mask clusters of change that is larger than 1 hectare. And so the algorithmic challenge is how to reliably detect change in a time series of Sentinel-1 data with noise and maybe a seasonal cycle. So we use this recurrence quantification analysis because it can take the order of the time series into account, because that gives a lot of information. Here in the bottom you see in red the time series, or the aggregate time series of 5 by 5 pixels in a, or 3 by 3 pixels in a forest change site, and in green you see the time series of a stable forest, and you see that some differences, but in gray you see all the pixels that are going into this average, and you see there's a lot of noise, or I mean, every pixel is behaving a little bit differently, but basically we want to do an analysis on the highest spatial resolution. So what are recurrence plots? So the idea is we have a time series, and now we can look at so-called recurrences. So in the bottom you see the recurrence plot, which is basically we compare every time step against every other time step, and then if they are in a certain threshold, so they are quite similar to another, we make a small black dot. So this is a recurrence, and then as you see in these examples, we can see there are certain patterns emerging depending on how our time series looks like. And the middle one is basically what we would expect to see in a clearer forest change event, where we go from a higher value with some noise to a lower value with some other noise, and but there's this clear distinction. But of course we can have also seasonality in there and so on. And now it's nice to look at these plots, but then we also want to derive statistics. So we take the trend, which is basically, we had this on the I think here, can I take the laser? No, I can't. Anyway, so you see these diagonals, and the main diagonal is basically every point against itself, and then you have points which are basically the same distance apart in time, and we compare, or we do a correlation of the number of points on these diagonals against the distance to the main diagonal. So, and then, so basically this says how much does change, or how much does the number of, or the likelihood that some points are recurrent depend on their distance in time. And if we do these computations and we plot this, we get plots like this, and then we can do a correlation. And if we have so in the first example, you see there's some changes, but this is basically the same over all the time. And in the last example, you see a clear line down. And then we take the slope of this correlation as our measurement of trend. And in a real world example, this would look like this. So we go here from the time series to recurrence plot to a map of these recurrence trends, and we see the change events are clearly visible in these results. But today I want to more focus on the algorithmic challenge and the deployment. So the problem with this algorithm was that basically we had to compute this recurrence plot for every pixel. And this is basically a spare matrix that is taking some memory that makes it slow to compute for larger areas. So in the middle you see the number of allocations that we did on the first initial algorithm, and then we basically removed this need to compute the matrix, or we kind of had to compute it because we need the values, but we don't have to save it all the time. So we basically went and saved and computed the number of points on each diagonal directly without going through the matrix, which then with a few other improvements in our computation reduced improved our runtime by a factor of 10 to the power of 4, and it also reduced the allocations by, I think, so this is on the right, you see in yellow it's already still already an improved version, so you see it, we reduced the allocations from 10,000 per pixel to basically 0, to 0. And this makes it much nicer and much faster to compute. And also the memory footprint of our algorithm is much lower. So then we also we wanted to host this. So we decided to use EODC for that because they have the Sentinel-1 preprocessed data that is already stacked in time series tiles that are already all on the same grid, which made it, at least as an initial step, easier for us to work with. And then we had to also, because the data is tiled, but it's still in the scenes, so we had to basically mosaic all the data together so that we don't have strange gaps in our time series. But these are just a few tricks or steps we had to do to make this work on scale. And then, yeah, just to say again, the benchmark results from going from an initial phase of already removing the matrix computation, but then also just doing some improvements to the code, also reduce the memory allocations again, remove the memory usage, and also remove the computations in time by roughly 25%. And then, so to deploy this, we are currently exploring ways to extend OpenEO. So because the analysis we did in Julia, so there's no Julia backend for OpenEO. There's no easy ways to deploy this currently, and so we had a look into OGC API, but and common workflow language, but also wanted to try using OpenEO for that, because with that we can have, like, there's all this machinery already that would take care of the billing, which would take care of the data deployment. And so we took our Julia code, we compiled binaries using static compiler, and then we wrote Python bindings for these binaries that are basically have a C interface, and then we managed to add this as an OpenEO Dask backend as an experimental process. And then you basically get that in this web editor, so that you can select your spatial extend, you can select your temporal extend, and then this goes into this reduced dimension, which then can call this RQA deforestation function, which then would give you some results. And of course, this is not what I did all by myself, so this is a small team behind it. And as a last conclusions, and I think what we learned is at least the algorithmic improvements are much more important than throwing more compute power on it. So we reduced the computations by huge factors just by improving the algorithm and only computing the things we actually need at the end. And also the deployment kind of works, but I think it's still a bit clunky, and there might be improvements there. And I think now, as an outlook, it would be interesting to explore how we could bring this to CDSE, and also how we could bring this to other data streams that are not as streamlined as the Sentinel-1 data that we used for this in EODC. And now I'm happy to take your questions.
Thank you very much, Felix. Are there questions? Yes, there's a question in the room.
Thanks, Felix. Great advocation for using Julia and geoscience analysis. Wouldn't it be cool to have a Julia backend for OpenEO?
Yes, it would.
That would be really fast, wouldn't it?
I would hope so. I mean, and yes, I think it would be nice. We have a lot of the components already for computing things, also in the Julia and Julia Geo. So it is just being to be wrapping up or parsing the OpenEO and making that convert that to something that the Julia system understands. But yeah, would be nice.
Thank you. Other questions?
Hello, thank you very much. Just a question, why wasn't it possible to use discrete Fourier transform to get this recurrence plot faster?
Can you repeat it again?
Couldn't you use discrete Fourier transform to get these recurrence patterns faster? Or is it not possible because you need to load all the data simultaneously?
I don't think I can follow. I mean, I don't think how would you use discrete Fourier to compute this?
Sorry, from the images. Okay, we can discuss later.
Yes, I think we should discuss this in the coffee break.
Okay, thank you.
Thank you. We have one more minute if there's any other question in the room. Maybe one from my side, Felix. Can you comment a little bit on the challenges for reusability or reproducibility of this workflow on other infrastructures other than EODC? So the portability of the method.
So currently the main, so if we want to use, I think now with this Dask process, or with this deployment with the binary, you could theoretically put any time series into it and reproduce it, but so for us it's just, I think you need this time series that is already stacked on a pixel level. That at least when we looked into it in a year ago, it was easier to use the UDC one, but I think that might have also changed, and I think as long as you get a time series of your measurements into it, then you can just use it also on other platforms. And we also wanted to, I think, with that, especially with that algorithm, it would be interesting to explore doing the analysis in radar geometry rather than local ground geometry, so that you don't have this pre-processing necessarily to do.
Thank you.
All right, thanks.
Okay, thanks again. Let's move to the next speaker.
So our next speaker is Anton Kostyukin. It's also about forest monitoring using Sentinel-1. The title of the talk is Preparing for a Three-Dimensional Sentinel-1 Towards High Accuracy Forest Monitoring via BiDS'25 SAR methods. The floor is yours.
Okay, thank you. So I think Felix gave you a very nice overview of how you can use Sentinel-1, like the current configuration to monitor the forests. And I will tell you about what the future of Sentinel-1 might look like. So I'm a first-year industrial PhD student from Estonia, and I do this work together with the University of Tartu and a company called Kappa Zeta. And I'll be telling about high-accuracy forest monitoring using BiDS'25 SAR methods. So the problem is that, let's say, currently there's a very high need for the forest monitoring, specifically because of growing demands for biomass estimation and carbon accounting. There are also green transition initiatives around the globe, but currently existing methods for forest height estimation basically result in data to be fragmented and localized. And the decisions which are taken on such data basically unreliable, because deforestation and afforestation area might remain unaccounted for, and basically that leads also to wrong climate estimates and, well, in case of carbon trading, financial loss. And one of the important forest parameters that you can estimate using satellite aperture radar is height. So if you have a bistatic or multistatic configuration, which implies that one satellite is an active signal emitter, and there are two or more passive signal receivers, then using phase information of the received signal, it is possible to obtain the height over the ground at which the signal was reflected back to the space. And well, SAR has, let's say, clear advantages of being independent of the weather condition, let's say, mostly. And it also provides large-scale monitoring with these. There are also quite a lot of studies which have proven that such method is actually feasible, so you can get the forest height. But what we found out is that a lot of studies, let's say, omit or do not mention some of the details. Like you may not find, let's say, information about the study area they used, so you don't know what was the tree height, like what's the forest composition. And we see it as a very significant research gap, and we want to fill it by basically systematically studying effects of forest parameters, so height, tree types, density, as well as data acquisition properties on forest height estimation. And we start with two study areas in Estonia, Saaremaa and Pikknurme. Pikknurme is one of the very well studied forests in Estonia, and we have 39 tandemix images, thanks DLR for acquiring them for us. They cover leaf-on and leaf-off conditions of the forest for year 2024. and they also have various sensitivity, which allows us to have a, well, pretty much diverse data set, even though the amount of data is not very large. We do processing, let's say, using open source software, so ISA-SNAP, and generally the flow is sort of known to the people who are in the, who are familiar with SAR. And I'll be talking about the SAR height and coherence, this red and green columns, because these are one of the most interesting, let's say, data rasters that you can obtain. And I mentioned SAR height, so you can imagine it as a scattering point over the ground. And then coherence is basically a measure of similarity between two images. I'll come back to it later, but we'll start with SAR height. So on the right, you can see those forest compartments in yellow and red color, which basically represents the height. And now, if we zoom in to, let's say, a couple of forest compartments, as we were doing quality checks on the data, we found this interesting case. So a couple of privately managed forests, and if we make a profile of the SAR height raster, and between the points A and B, you see there's a very visible response, pretty much, which also grows as the forest gets thicker and it gets taller. I'm not sure if it's visible from back there, but like around point A, it's very low, and it gets much bigger at point B. And then between point C and D, something goes wrong. Like on the left image from 2022, you see there's a very thick forest visibly, but where is the timeline? And it turns out that a year later there was a clear cut, which then resulted in trees started to slowly regrow, and we are having a very sort of small response of around 1 meter around that area. And that basically brings us to the topic to fragmented and localized data. So you have to be very careful even when you're doing basically quality checks. But now if we take this data and let's put it in the random forest, because we want to predict the forest height. And we chose random forest at this point due to its simplicity, low data requirements, so we can put as many features as we want within, let's say, reasonable limits, as well as amount of the data. And for the input of random forest, we use quite a lot of auxiliary data, so basically geometric information about the scene which we can derive. So I will mention latitude and longitude separately, but basically some aspect, elevation information, slope. We are using backscatter, SAR height, derived rasters, and coherence. So this backscatter, SAR height, and coherence are also polarization dependent. So in total, we are getting around 20 features, depending which ones also we decide to take. And on the right, you see the results only for the birch dominant forest compartments. And this is feature important. So basically, which of those covariates contributed the most to predict the forest height. And generally, we see that the SAR height is one of the main contributors, which makes sense because it basically reflects the scattering point. And that basically also supports the findings of the previous studies. And we see that coherence is sort of also catching up, let's say, on the importance. But what is a bit suspicious we found is this elevation and incidence angle of a relatively high importance. And we believe is that the sampling technique was not very optimal at this point, because this was one of the very first runs of the model. And also considering the R2 and mean average error scores, so the model probably overfitted, and there was spatial autocorrelation probably included as well. But for the future, so we plan to make the methodology more robust and more open. So we would like to employ more, let's say, reasonable sampling technique, so that perhaps some of the forest compartments do not end up in different data sets. This also will possibly reduce the spatial autocorrelation, especially for latitude and longitude, which was very high, and that's the reason why it was taken out from here. We would like to employ different forest properties. So we have forest registry data from Estonia, which has information about different tree levels. So if the forest is, let's say, moderately old, there might be very tall trees and a little bit, let's say, trees in the middle. So we have information about that. We would like to explore more about pixel versus compartment-based model, which we haven't really seen mentioned anywhere in the studies. And sort of pros of the compartment-based model is that coherence is usually estimated over the area. And because our image is very noisy by default, that might actually make it more reasonable and more robust, especially in case of coherence. And we plan to scale up for a bigger area, include Finland, Norway, perhaps Latvia as well, but that's, let's say, plan for the future. And as I mentioned before, the work is done by Kappa-Zeta. This is Estonian observation startup, primarily works with agriculture, forestry, and recently also with the defense applications, together with the University of Tartu Landscape Geoinformatics Lab. And we primarily sort of work with the spatial machine learning, which, well, the university are experts in. And I previously mentioned there is a scientific interest in this study, but also there's commercial interest, as in Kappa-Zeta we want to build basically a satellite mission, and the goal of which is to put 3 passive receivers next to Sentinel-1. And that will enable us to have a cross-track interferometry, and because there are 3 passive receivers, it is 3 different baselines, which allows us to have different sensitivity. We have concluded phase 0, and we're moving to the phase A with ESA, and we really hope that this might be the bright future of the Sentinel. And this is it. Thank you for attention, and you can come to Landscape Geoinformatics booth and learn more about the work that we do. Thank you.
Questions? Meanwhile, I have a question. There's one.
Thanks, Anton. Great talk. Could you maybe, if you have some information about the mission, how this could go forward, like who's building then this additional satellite?
Yeah, so I'm not let's say a hardware person. I'm on the software side. We have a technical team who is dealing with this. But I think at the moment we are looking for the basically for the subcontractors. We are looking for the launcher. Like ESA prefers the European launcher, but there are also options for the US based like SpaceX and Rocket Lab. But let's say the rockets are different, so the prices are different, and we have a separate team who is looking into that. But there are no, let's say, defined companies at the moment.
We have time for one more question. Can you tell us something more on the customers? You were saying you were planning to upscale, you would like to do it on national scale. Who would it be for? What are the applications you have in mind? It's a startup, if I understand well.
I mean, officially yes, but the company is 10 years old. It is a spin-off of Tartu University of Observatory. The clients-wise, we have PRIA in Estonia, and at the moment we provide quite a lot of services under CAP policy, this Common Agricultural Policy, about basically mowing, plowing, and now it also will include clear-cut detection. And if we have this like very sort of constant revisit time, which Sentinel-1 already provides, And now if we make it three-dimensional, then it basically allows us to make all these applications even better, even faster on a more regular basis. And at the beginning, I also mentioned the carbon credits. So a couple of years ago, there was like a big issue with one of the biggest certifiers, I think Verra, I'm not sure actually what's the name exactly, and that their methodology was not, let's say, very much bulletproof, and it turned out that quite a lot of those credits were worthless. So if you make, let's say, estimates for the future climate, and these estimates were actually wrong. So the companies actually were, let's say, polluting the atmosphere even though they were expecting not to, or at least were told that it won't be happening.
Okay, thank you.
Yeah, thank you.
Okay, so let's move to a completely different topic on space operations. So we have the next speaker, Miguel Teodor Munoz from GMV.
Yeah. We're running a bit late, to be fair. But
The floor is yours.
10 minutes late.
Hi, so we are going to present our tool for anomaly detection in telemetry data. Is it called BiDS'25? Let's begin with the introduction of the problem. So why anomaly detection matters in spacecraft missions? Spacecraft missions rely on many data, given many telemetry data are collected by different systems, and satellite operators cannot rely on manually inspect all of them. They are hundreds of interconnected time series, so it's impossible to manually detect even a subtle change on the pike of the signal. So the growing complexity calls for a more advanced data-driven solutions, and AI can automate anomaly detection, enabling faster, more accurate, and cost-efficient operations. So scaling anomaly detection to emission-level data, here are some numbers that you can see that every month a single mission can generate. So it's up to 1 million of telemetry records, 20,000 parameters across multiple subsystems, and 72 gigabytes of raw data to process and monitor. So traditional rule-based approaches cannot handle this level of complexity. And how can we efficiently detect anomalies in such massive multivariate data systems? Let's see. Let's present our solution. So BiDS' is an unsupervised anomaly detection system designed specifically for industrial processes, but also for spacecraft telemetry. The purpose of using this solution is to detect anomalous periods in multivariate time system series and identify the most contributing channels. So we would like not only to know when anomaly has happened, but also which channel has created that anomaly, or which subsystems has failed on that anomaly. It is based on a multivariate statistical process control, and also in principal component analysis. As I said, it's adapted from industrial process to space operations. That is the workflow BiDS' is following. So we get the data, then pre-process them, then model the BiDS' tool, and then after a post-processing period, we will get the results. As you can see here, this is just how BiDS' will show that some values are exceeding a threshold, indicating that we have an anomaly for those dates in the satellite. Using this graphic, we can also generate the one that tells us which channels has been involved in the anomaly. So this was just an introduction. The first thing that we need is a data set of telemetry data. We didn't have any good data sets until last year when ESA released the telemetry data open source data set. It contains data from 3 missions. 2 of them were used for benchmarking. And it contains more than 10 years for the mission 1, 3 years for mission 2, and I think it's almost 3 years for mission 3. This data set has been analyzed by domain experts and also annotated by them and cross-verified with state-of-the-art algorithms. It simulates real mission conditions and includes a hierarchical evaluation pipeline. So we can use it in our tool and to compare it with different anomaly detection algorithms that can be studied in the literature of the paper released also by ISA along with the dataset. OK, so once we have the data, we need to preprocess it to have this data prepared for the ingestion of our method. So we need to do 2 things with this kind of data. That is a resampling, because different sensors has different frequencies of sending data to the ground control centers. So we need an unified data set with the same frequency for all sensors. So this is the resampling part that you can see here in the graphic. In red is the raw data. So for each channel, we have different frequencies. Then after resampling, you can see in green that all the channels has the same frequency. And we are also applying a zero-order Holt interpolation modified method. So we are filling missing values by propagating the last known value without using future information. And also, even if the last known value is not an anomaly, but there is one anomaly preceding to this value, we are taking the anomaly. So we are not missing any annotated points on the dataset. So this ensures a clean, uniform dataset ready for anomaly detection. The impact of having preprocessed this dataset is the reduction of memory consumption and the storage of this in a cleaner way and in a most feasible way for our common use of it. After we have prepared our data, we are going to train the model. So PITIA learns, PITIA is performing anomaly detection through a dimensionality reduction approach based on principal component analysis. Also, it uses multivariate statistical process control techniques. What we have done is once we train our model on this data, we project each new observation onto the principal component space, and we see how much it deviates from these spaces. So we are using for the principal component analysis 90 to 95% of explained variance. So here you can see we reduced from 76 channels in mission 2 to just 8 components using PCA, and it has more than 95% of explained variance. And then to detect anomalies, we are using 2 main statistical indicators. One is the Hoteling's t-squared that measures how far an observation is from the center of the learned PCA space, and the main one is the square prediction error that measures how much of the observation cannot be explained by the model. So to determine if some event is an anomaly or not, we see that the SPE exceeds the upper control limit that is computed based on a chi-squared distribution with 95% of confidence. And if the SPE exceeds the upper control limit and the t-squared exceeds the threshold, it is flagged as an anomaly. But the thing is that this upper control limit cannot be taken just by itself, because we have seen that when two anomalies occur in a very small amount of time, they are not. We only catch the first one, or the highest one. So after we have trained our model and computed this, applied the PCA, computed the SPE and the Hoteling's T-squared, we apply a post-processing step. That is, it consists on one hand a refinement. So instead of using the SPE itself, we use the gradient, the absolute value of the gradient of this SPE. So when we detect big changes in over time in this SPE, it means that we have two different anomalies. So as you can see, initially using only SPE, the first part of the graph shows that it's only one anomaly that extends that long, and applying the absolute value of the gradient of the SPE, we can we can see that we have two different anomalies in that amount of time. So yeah, instead of using the SPE, we are computing the gradient of the absolute value of the gradient of the SPE, so upwards or downwards, we are going to catch all the close anomalies. And also, after we have seen where the anomalies are, we have to group them if they happened in less than 6 hours. This is not a fixed or arbitrary value. This is based on our domain experts, on satellite control centers. And yeah, we consider that if they happen in a period less than 6 hours, they are considered to be the same anomaly. Together, these post-processing steps significantly improve detection reliability. Then, after we have collected the data, pre-processed them, trained our model, and post-processed the results, we have to evaluate it against the ESA benchmark for different anomaly detection methods that they have proposed. Some of the metrics they have used are these three. They also have more, but for brevity reasons, we are going just to focus mainly on the first one, that it's event-wise, that it's F0.5. So it's a trade-off between precision and recall, weighting more precision. That it means that we need to minimize the false alarm raised. So yeah, this is the metrics that ESA released, and then we are going to compare our results with the ones that they have published. So we have trained our model in mission 1 and in mission 2, and these are the results that we got. We trained on mission 1 for 84 months and then tested on 84 months and 21 months. As you can see, there is a gap of 3 months between them. Those 3 months are used for validating, same as in the ESA paper. And in mission 2, since we have only 3 years, we have used 18 months for training, 3 for validating also, and then 21 months for testing. As you can see the results, in mission 2 we we succeeded. We got the highest punctuation on this experiment. They have also more experiments dividing in steps, but we focus on this one. So in the full set of channels, we got the highest punctuation. That it means that our model is very robust. And in the subset of channels, we got the 3rd position, meaning that it can be, it has a very good adaptability to the reduction of amount of channels. In mission 1, we got very good results also, but Telemann is approved, got the best solution. It was made ad hoc for this experiment, and it's worth to mention that this method needs more than 8 hours to be trained. In fact, our method took like less than 10 minutes for these experiments. And yeah, these are the results evaluated on the same benchmark that the ESA proposed. But this is not what we wanted to show. We are not competing against ESA. We just wanted to see how it performed with different methods. The thing is that with some unanswered question raised that it's like, okay, should we retrain these models? When the retraining should happen? Do we need 7 years in mission 1 or 3 years in mission 2 to be able to train a model and apply it for our data to see if we have a very good method or not? And the thing is that PITIA, as I said in the beginning, it's an unsupervised method that it doesn't need labels, and it doesn't need a big amount of data for be trained on. So our main strength here is that we can use only 1 month on training, 1 month on testing, and then applying a sliding window of the same amount of time. So we are sliding 1 month each step. So we can retrain the model every month. We don't need a big amount of data. We are up to date with the new changes that could happen in the missions. So from benchmark to operations, this is how we are expecting to use PITIA on a continuous retraining model. And yeah, the conclusions are that we have a very robust and scalable approach for our method. It's valid in real scenarios with large volumes of data. We have trained it with 7 years for mission 1. It's generic, valid for different missions, signal types. We have also trained in different data, not only for ESA. We have applied it to industrial process. It's unassisted. We don't need any action from the operator, so it works on unlabeled data. You can see if an anomaly has been raised. Low computational requirements. I've run it in my laptop, so you don't need good amount of expensive hardware for running these models. Adaptability to changes, and well-balanced results between precision and recall. And also, it is not said here, but it's very lightweight, and the time it takes, it's less than 3 minutes for processing up to 1 year of telemetry data. And the results that we get for benchmarking is outstanding results for mission 2, especially when training by subsystems, and promising and state-of-the-art results for mission 1. This mission seems to be more stable and refined, and its anomalies more unstructured and challenging. So, yeah, this is everything from my side.
Thank you. We ran a bit over time, but if there's a quick question, we could take one. Okay, please reach Miguel in the break. Or do you have a question? No? No. Okay, thank you again, Miguel.
Thank you.
So our next speaker will talk about EOEPCA. I'm not sure if I'm pronouncing it correctly.
Yep,
it's about open source Earth observation data exploitation platform.
Thank you very much. Oh, yeah, I need that. Hi there. So I'm Richard Conway. I'm from Telespazio. And so EOEPCA, EU Exploitation Platform Common Architecture, is an ESA project. So Telespazio are leading that, but supported by many what we call domain experts, companies that are developing the building blocks we produce. So just a bit of context, what we mean by an exploitation platform. So we define it as a virtual analysis environment that has access to data, provides compute and other tooling, and it's really designed to support collaboration, sharing, and publishing. And most importantly, it's contributing to this value-adding chain in which the data, the mission data perhaps at the bottom, can be transformed into actionable information at the top, information that is then used by decision makers. So we define various capabilities of an exploitation platform that would be required to support that. So from discovery and access, through processing, maybe providing analysis-ready data through data cubes, supporting machine learning, and then as you reach the CHOP, we're talking about clients that are able to make that data available and present it through dashboards, and thus supporting this decision-making process. In terms of, so how are we tackling? So the problem that has been perceived is that there are many such platforms. I'm sure you're aware there are many data and processing platforms, but there's quite a fragmented ecosystem amongst those platforms, and therefore it's difficult for users to pick and choose and maybe combine the capabilities of those platforms into whatever their workflows are through this data transformation process. So to tackle that problem, the common architecture is our approach. And what defines the common architecture is we are providing these capabilities as services using open standards. And therefore, that encourages, we hope, federation through those open standards amongst the platforms and their EO offerings. And also, therefore, interoperability amongst those platforms, which again facilitates those users to traverse across those, that ecosystem that exists. So we have an architecture that defines this approach, but we also have a reference implementation of that. So a whole load of open source tooling, building blocks as we call them, that are very much designed to be reusable. So the idea is that you can take these open source components if you're building a platform, and you can pick and choose and build them into your platform offering. This encourages the interoperability, but also, hopefully, we're reducing development costs by providing this reuse. You can see across the bottom, we have a timeline. The project's actually been running for a few years now, since about 2020. 2 phases, so we're now in phase 2. So briefly, what's phase 2 all about? So we called this EOEPCA Plus, very much just building upon what we had done in the first phase. Similar goals. These reusable building blocks, but we just took the opportunity at the start of phase 2 to sort of step back, appraise what had happened in phase 1, decided what had worked and maybe what hadn't, and use that as an opportunity to sort of refresh our offering. As part of that process, we've tried to engage more with what we call stakeholders. So these are actual platforms that are committed to uptake our offering to make sure that we're well understanding their use cases and so reflecting that in our developments. And also, to improve our open source credentials, we've joined OSGeo as a community project, really to make sure that we have good governance around that these open source projects that we have. And you can see there, we also identified a few new capabilities, but we'll see those as we go through. So, what do we mean by building blocks? It's a term I've used. So you can see here the diagram on the right, that's broadly speaking the architecture, sort of in one snapshot. And we combine these building blocks into this architecture. So what do we mean by a building block? It's a software component, typically that has a capability that's delivered through a service, these open standards. Typically a REST API, depending on the standard. They're designed to be used on their own, so you can pick and choose, but we also offer a bit of added value, hopefully. We offer a way of combining them into a slightly more integrated platform. They're open source. In terms of the software stack, we target Kubernetes, which gives us a nice sort of abstraction away from any particular cloud environments. They're all containerized, and we deliver those through Helm charts for Kubernetes. So I'm going to try and quickly run through the building blocks. There's quite a few, so I'll have to go quite quickly. First of all, focusing around data and resources. So building blocks for discovering, access, and management of data and resources in the platform. So first, our resource discovery building block. And this is not just about data. This is very much about open science. So that brings in all sorts of resources. So we have workflows, of course, data sets, but things like notebooks, machine learning models, training data, all of these artifacts that contribute to open science. We want to make sure that they are discoverable and therefore reusable in that sort of reproducible environment. So we have the discovery building block, which offers a stack, an API records discovery interfaces. Then we move on to the more specifics of data. So we have the data discovery and access and the data access building block. So this is very much around the discovery of the data. So we have stack interfaces and then the exploitation of that data. So for example, the tiles API. By the way, you'll notice on the slides I've scattered around various logos of the different open source projects that contribute to each of these solutions. So this is very much built around EO API, so we have T-Tiler, and also we have support for features within that environment. So that's really exploiting that data. Then we move on to support for analysis-ready data, so via the DataCube access building block. So this is something that came out between phase 1 and phase 2, very much a sort of a new offering. So this is all about pixel-based access to multi-dimensional data, really supporting that sort of analysis use case. So in a way, this building block is, as much as anything else, a consolidation of other complementary APIs. So we have Stack that is describing the data, let's say, through its metadata. Then we have the tiles interface, again, for being able to render some outcomes. And then that's supported with OpenEO, but also other sorts of processing in reality, providing synchronous, fairly quick analysis on that data through, band math and that sort of thing. To facilitate this, we've very much focusing around Stack for passing data around, and so we are working on a best practice specifically for data cubes and describing those through Stack. All of these services that I've discussed, they obviously need the access to those resources and to that data. So we have a resource registration building block, which is responsible for harvesting, and it integrates, therefore, with external data sources. It has a generic approach through harvesting through Stack, but also it is extensible, so it's able to support integration with other sorts of data sources. With that in mind, we also have the data access gateway building block, which is built around EODAG. You may have seen that earlier in the week, and that provides a sort of an abstract interface and supports many data providers, and we're therefore able to exploit that within our harvesting component. And also, we're hoping to support the development of EODAG with additional providers as our stakeholders demand them. Then moving on to the processing side, so there's a collection of building blocks here that's very much around bring the processing to the data, which is what makes it the exploitation platform. So it's about user-defined analysis. So there are two main processes here. In phase 1, we were very much following the OGC API processes pathway with application packages, and this is very big for us still, so we're still very much following this approach. Very quickly, the OGC application package we define it as a portable processing workflows. So it uses common workflow language, CWL. The steps are containerized, and that's really what gives you this portability. There is an OGC best practice that describes the use of OGC application packages in this way. So then the building block, the API processes building block, is provided by the Zoo project. It supports that API, including the part 2 of the API, which is very much about the ability of users to deploy their own applications for execution, their own workflows for execution. And importantly, along the bottom, we have a number of backends that allow you to integrate this into your platforms. So Kubernetes is the core, if you like, using Calrissian, which is the workflow runner. But also we have integrations for HPCs via Toil and Slurm, Argo workflows, and also Dask as well. So you can define an application package that has a Dask requirement, and we can spin up a Dask cluster on demand to support that. OpenEO, so this is new to us. It's not new to the community, we know, but it's we've embraced it, if you like, under the EO-EPCA umbrella. It offers a complementary approach, I think, to API processes. It's more client-oriented, very closely oriented with the data that's provided alongside it, and it provides that real sort of easy analysis approach for interacting with the data and transforming the data. Similarly, it supports some different workflow runners. So we have an implementation with a Spark backend and also for Dask as well. And then finally, at the bottom, something that we're currently trying to work through is this idea of the federated orchestrator. So this is really taking these workflows, both approaches, and finding a way to orchestrate the steps of those workflows in a hybrid way across platforms. So we are, for example, for data locality, you know, if you have particular parts of your workflow that are suited to different platforms and different data offerings. So that's really trying to bring all of this processing concepts together into one place. And then finally, the workspace building block is quite important to bring all of this together from a user's point of view. So their processing outputs need to go somewhere. So we have a workspace building block which provides storage, a way of managing buckets, interacting with buckets, setting up sharing so you can share your outcomes and that sort of thing. It also has vCluster, which is a way for users to actually run their own services and deploy their own services within the platform environment. And importantly, there's this feedback loop that then takes these outputs, the workflows and the results, and pushes them back into the data discovery that I talked about earlier, and therefore that's providing the open science. Then they can be discovered by other users with enough metadata that's describing them so that they can be used reproducibly. I focused on those two areas just to give the core flow, data and processing and resources, but there are some more building blocks I can quickly mention. IAM is important, so we have an IAM building block that supports obviously access control, but also sharing scenarios in this collaborative environment. Machine learning, so we have a machine learning building block to support training and data management. The application hub provides a notebook environment and other applications for dashboards and also supporting application development. There's an application best practice building block, quality building block, which supports tooling around best practices for application development, making sure the code quality is good and that sort of thing and performant. Event-driven behavior is about improving the internal communications amongst the building blocks, but also supporting automated behavior, triggered, systematic processing, that sort of thing. And then finally, the resource health BB, this is motivated when you have something that's produced through all of this preparation and analysis, you're then able to expose that as a service, and the resource health building block ensures that the health of that service. So if it's either a data offering or a processing offering, it allows you to automate tests against that with notifications when there are issues. I'll quickly click through this. So Telespazio are leading this, but we have many partners, our domain experts. So you can see the little boxes for all the different building blocks, and you can see all of the partner organizations that we have here. There are many. We have a really great team. Many of these are operating their own platforms, so they bring their use cases into this and their expertise, and that's helped us to guide the way in which we've designed these building blocks. This is some of the team. This is at LPS. This is our OSGeo page. And yes, these are just some of the people. Some of them are here, but there's many more people involved. Very quickly, if you want to follow up, then we have a number of online resources. We've got documentation on Read the Docs. We have everything's open source, so we have a GitHub organization for that. And we also more recently have developed some Killer Coder tutorials. So these are web-based tutorials, and you can just go to EOEPCA at Killer Coder, and you can find these tutorials, and you can have a play with sort of deploying and understanding a little bit more under the bonnet what these building blocks are all about. Just to very quickly mention that my colleague James this afternoon will do a quick demo of one particular aspect of what I've described here around processing. So that's at 5 to 1 in the demo area downstairs. And that's all I have. So I can just leave a few QR codes to some of those resources, and hopefully I've met my time.
Thank you. In the interest of time, I suggest we will not take questions here now, so please approach
Okay, thank you.
In the polls.
Okay, so I'd like to welcome the next speaker, Laura Poggio from ISIRC, World Soil Information.
Okay, thank you very much.
Welcome.
For the introduction. Today I'm going to talk about some of the methodological and computational challenges of integrating high-resolution Earth observation for soil property mapping. I am speaking more from the point of view of the user, if you want, of a lot of the tool that you are developing. And now we are going to use the result out of these tools into further processing. So first I would like to briefly explain the main ingredient of these processes. Is called digital soil mapping. Is a kind of regression machine learning approach in which we have training data, we have covariate, mostly defined from remote sensing, but also digital elevation model and climate. And then we have a predictive model. Right now we use a lot random forest and quantile random forest, but there are a lot of development with neural network, and there is a lot of work also with reintegrating geostatistical models into this. Then we get some maps, so a continuous surface from the training data. And then we need to evaluate them, because these are content map, and the expert on this content need to be sure that this map makes sense for them on the ground and not just on some numbers on a paper. So, and to do this, we work a lot with the user. So first of all, we ask what the user wants, and this was a quite interesting survey from a small project of the FPCAP framework, in which we asked which is the resolution that you prefer. And most of the users asked for 10 meters, and we had the feeling that it was because Sentinel is at 10 meters, so they thought that that was the resolution we could do. And when we asked which was the next one, they went to 20 meters. But sometimes it really depends on the test case and on the user case. So what are the challenges in this domain, especially in the latest couple of years? We have more and more remote sensing data at final resolution. It's really a huge amount of data. And we need to process this data, and we need to assess if this data make the results more accurate, realistic, useful for the user, or they just give a false sense of accuracy. And especially, we need to make sure that this integration of remote sensing is scalable and make use of the open source data and open source code. And we need to evaluate critically the outcome, because a lot of the training data for these models come from the 80s, and sometimes they were georeferenced in a square of 1 kilometer if we are lucky, or of 1 degree if we are less lucky. So are we using all these data? Can we use all the covariate that the model can handle? I mean, if we talk even about only optical indices, we can create 400, 500 in one go. Or is the most complex model or the ensemble model or some simple point-wise evaluation? From a computational point of view, we try to work in a fair way. So I try to summarize the main challenges with Findable. Hopefully, both input and output are in data catalog with metadata. They need to be accessible, so we try to make input, output, and code with persistent metadata and documentation freely accessible, but often with the soil data is difficult because right now they are considered a bit like national security information for food security and a lot of other options. Interoperable, we use standard format from OGC and other interoperability agency, and what is important is reusable. We really look to reproducibility, both from a scientific point of view, but also from the user. They need to know how the data were produced, because it's linked with trusting the result and using this data for policy making. So this is the workflow that we develop and we're using. From what I saw in the past couple of days, it could be considered, if you want, the poor man implementation of a lot of the cloud-based workshop that I saw. But what we're trying to do is we work with container. We need very specific geospatial tool, often are of course GDAL and a lot of grass, and then we use this container on a scientific-based HPC from a university using workflow manager like SnakeMake linked with Slurm in order to manage the different steps and the different computation. So the main principle is Linux and open source base. We make use of a lot of the geospatial library of GDAL, GeoSproj, and we use them compiled from source because it's less painful than trying to convince the different versions to talk to each other. And we use modeling tools. I know that R is not the favorite, maybe, in this venue, but it's useful for a lot of the statistical tool. And personally, I think GrassJS for science and for some of the processing is still one of the most powerful tools out there. And then, yeah, containers are useful, containers are wonderful. Singularity and Obtainer that are making this container workable on HPC without the administrator complaining too much is a great support for us user scientists to use this. SnakeMake and Slurm, when they talk to each other, really make the life easier to manage this workflow, and is, if you want, cloud agnostic ready because we have containers, and once the container can be run with different workflow manager. And yeah, there are sometimes big containers, but this helps us a lot into managing our workflow. So the main operation are the data preparation, the input data. The input soil data is really still mostly manual process. And for the covariate, we are Google Earth Engine, OpenEO, local parallel processing with whichever tool we like. Then we need to train the model. We can do in parallel with combination of hyperparameters. Prediction can run full in parallel with geospatial tile. For Europe, 20 meter, we're talking about 10,000 tiles, sometimes more. And one bottleneck that I really hope Stack will solve is the mosaicing of the tiles, because a lot of our users want a cog. They want cog for the wall of area. And if I have to prepare a 20-meter cog for the wall of Europe, yes, I can, but it's not the most efficient way to both serve the data and to share them. But when it gets interesting is when we go to the post-processing and the evaluation of these maps, because the previous steps are quite standard, but in the evaluation, tiles are not always possible, so sometimes we have to find ways to really get into the dynamics on how the soil maps and the soil vary across the area of interest. And these are 3 examples that I am going to explain briefly. So we have many maps, and we need to choose among these maps. For example, for some soil properties in Europe, we are now close to 15 different maps of the same soil property. And I personally get confused when I am the one that created maybe 7 or 8 of those, but for the final user is how do you choose? Because there are little difference. And if we look, these are 3 random maps from the 20 that I mentioned. If we look at the point accuracy, yeah, we have some difference, but it's not that big that we can say, okay, one is for sure going to be the best. They're quite similar, but when we plot just the distribution of the value of these maps, we can see that these 3 maps are different. They're not the same. So we need to provide the user with some information on which is the most useful for their test cases. And this opens a huge amount of computational issue on our side, because we need to process this large data set in a different way. And here you can see this was just a global variogram for the whole of Europe. Not great idea, but it still shows that we have different spatial structure in the map. But if you look at the accuracy, basically they're quite similar, but then they are not. So we are working on some option to characterize this map. One is the area of applicability. Is defined on the area where we enable the machine learning model to learn about the relationship on the training data. And we have some dissimilarity index calculating on the distance of the training data in the multidimensional predictor variable space. These are just examples, and we can see that it kind of makes sense pattern-wise. We have higher dissimilarity on the Alps in the mountains where we know we have less points. And this is kind of important both for assessing the maps, but also for saying, please go and get us more observation data in these areas. And in order to convince the stakeholder to use this map, we also need to make sure that at least some of the covariates that we are using are making sense from a biophysical point of view. And finding out the importance of the different covariates in the different part of the region of interest, in this case Europe, helps the expert to assess if the maps make sense in that area or not. And it's also important to find out which map capture the local variability of the soils. These are, again, variograms. These are 2 of the maps that were in that table, and we can see that, again, they are different. And what this means for the user is that they need to assess if the map works for their study areas or not. And then often with this method we have also uncertainty from quantiles, and this is quite important because this range can be quite wide. And this method allows to create a single map with the uncertainty encoded as the pixel size. So here we have 2 maps. What's coming from the same data. we have a low uncertainty threshold, high uncertainty threshold. Low meaning you are not willing to accept a lot of uncertainty in your map. You want to be sure. And all of a sudden, the resolution start to change. So the bigger are these square, the bigger the uncertainty was, and the fact that the map was produced at 100 meters is not supported by the uncertainty. Basically, we are saying that if you want 100 meters, you need to improve your model a lot. But if you have a higher uncertainty threshold, then there are more areas that support your original resolution. This is still a lot of work in progress, but is quite a visual way to inform stakeholders on what to pay attention to. Computational implication is that we have increased computation times and combination. Some operations are not easy to tile, and for what we saw about these polygons, we are really looking at billions of polygons. So as concluding remark, digital soil mapping is a complex data workflow, and is now computational and programmatically rather easy to produce many soil maps and increasing finer resolution if you have enough computation power. But expert knowledge is fundamental to evaluate the DSM product and make sure that such products are fit for use. And uncertainty and error propagation are crucial, and the evaluation maybe should go beyond the basic cross-validation, and even if it means that we need more computational intensive tools or more HPC-friendly workflows. So this was all. Thanks.
Thank you very much, Laura. I would suggest to reach Laura in the break because we're already 15 minutes over time and we don't want to keep people too long. So maybe the last speaker.
Hey, oh, okay, it's already on me. Cool. Hello, everyone. I'm the last speaker of this section. So I first introduce myself. I'm Yufeng He from OpenGL Foundation, and in OpenGL we dedicate ourselves to produce open source data, open source solution, fully open. So in this project where we have Open the Monitor, we are trying to persuade this kind of trail, and then we have this collaboration with University of Munster, Johannes, and Yasa in Luting, and today we'll present the work that we are doing together. So this is kind of like a ramp up of what we are seeing right now as scientific community embrace a lot of NS-ready data for SARS and optical, but the space-borne LiDAR, as what I'm currently working on, is a little bit drowning. And today we are focused on the big data from space. And one of the big data from space for LiDAR data is just space-borne LiDAR, and one of there is the mission of NASA mission JEDI. And JEDI have the waveform of the LiDAR system, and they start from 2019. Already use a lot of application for canopy mapping and canopy structure and stuff. And they have so far the data was recording here till 2022 is like 4.5 billion of laser scan record. And for each data set, like level 2 data, you have plenty of attributes. So in total, 94 attributes in there, and they're basically point-based of the data format, so it's not like a raster layer. So you can see the raster-like layers on the right side is very sparse in the case of not good to be a data cube in my point of view. And also, the LiDAR data is mainly a 3D representation of the surface. So in one record, you have so many different things that you cannot rasterize into a single layer, otherwise we create massive data layer with no efficient storage. And what we're doing this because we are actually doing a lot of global mapping. So the use case for my product already has been used for a paper to map the digital elevation model, and also some people already use JEDI to map canopy height, and also we have just recently published a paper on scientific data sets to map the shore vegetation, the vegetation height outside the forest using the global satellite LiDAR like ISAT to do this work. So it's related to what we are talking about, how do we organize this. So this is the basic format that we can get from NASA, the data structure of the JEDI. So you can see the orbit. The data has been organized in the chronological orbit-oriented format. So each data have the time record and the orbit and the track. So if you're really interested into some place, for example, this is my little Q Island, you were really interested in some area, you actually have to, you're interested in the area which JEDI has been passed through for the whole time series, for example, you have to query a lot of files that cover this area, and you can see that most of the area is not covered by the bounding box. And if I download those data, it just explore my data storage. So what is our solution now here? And we all know we have different style of the construction material. One is on the left side is tile, and the right side is parquet. And what is the difference between tile and parquet? So basically, tile is very regular shape, but the parquet is irregular, and it's really suitable for irregular data storage, especially that we are seeing near the point database. So that's the conclusion why we started doing this. So we adopt one of the open source solutions. It's Apache Parquet. It's a column-oriented data storage format designed for like efficient data storage and retrieval. And the first feature, they have good compression algorithm. Then they have partition features in the second. And also they support lazy loading, these cloud-native features. So this is actually the comparison, I think, done by Planiscope to compare different factor data format to do data storage and query. The speed for, you can see on the left side, using Panda to read the data is already 5 times faster. And the right side, the data storage is like 2 times more efficient than traditional data format for factor data. And the partitions is interesting. So what we're looking here, you can actually use the Parquet to separate the data according to different space-time domain. For example, here, you can define the data set. When you read factor data, you can partition to partition A, B, and 0, 1, and 2 based on the month. And also, you can do based on the spatial extent. So, for example, you're using this 30 degree altitude to separate the data into 3 different chunks. And also, you can combine these two to create the partition for space and time. And that is what we are actually trying to do for JEDI data, because the JEDI data is recorded as the chronological sequence, where we're trying to do parallelization computing. They have to communicate with each other. So it's very difficult to actually separate, to actually create some spatial temporal query for the small region. But using this partition format, I can actually define the space and time and put every data in the same space and time together using this partition algorithm. And also you can do it in parallel, because each file, they don't have to communicate with each other. They just being designed to end up in the same space-time block. I will show you the next animation that's more represented how it has been done. So first of all, you predefine the partition block as, okay, this is 1-3 block as an example, and the orbit will keep running through, and each orbit, each file that has been represented some track of the orbit will be read in the server, and the server will give the partition criteria based on the partition information. For example, D3 block, it can be, okay, the bounding box of Congo forest, and bounding box of Mongolia, and bounding box of Australia, to actually find all these points that fall inside the bounding box that I designed for them. And in this way, I don't need to communicate with each files when I do the parallel computation. And in this way, I can also reconstruct the file into spatial temporal block according to the partition algorithm. And so we have the algorithm set, and now we also adding a more kind of additional value based on the research that has been done for JEDI to reduce the noise by, for example, removing a low quality point and the JEDI, which is have the horizontal arrow, which is obviously not very usable for space for like height measure, because it's actually the same place as the geolocation located at. And also to increase to actually remove all the points with a lower sensitivity, because they don't actually have a strong confidence that they actually measure the right height. And using this kind of format, we can also, doing the streaming, we define some criteria to reduce the useless, the kind of like noise data to get a better analyzed ready level. And then in OpenGL, we have a computer cluster, so we can actually run this in the big cluster independently for each file that has been reading from the JEDI NASA format into a Parquet format. And then we're able to reduce the big data format and also combine the level 1 and 2 data into more analyzed ready level. It's only about 750 gigabytes of the data at the end in GeoParquets for this time frame. And so we also think that we also test a little bit about how the accessing time for this kind of partition of Parquet file, and we found out like a lot of different small chunk of the file will increase the reading time. So at the end, we not only streaming all this orbit-oriented Parquet file, oriented NASA H5 file into GeoParquet, we also aggregate all the small Parquet file in the same space-time block into a single one. And in this way, we can also do it in parallel because the block are already predefined. So we do everything in parallel, and then we derive the metadata for how many points in that, how many megabyte of the data will be in the spatial temporal block. And later on, we also designed a stack catalog to actually record all this block and all this metadata, and also go into the data entry point that we can see in this example, the JEDI block, that you can go to different spatial temporal block, and you can actually find the file. And there's no paywall, there's no things behind that. You can just download from there. Parquet also have the last feature I wanted to say. It's mainly used for, as I say, that there's a lot of attributes in JEDI data. And one of the good features is Parquet supporting lazy loading. So you can only select the column that you are really interested in, and you don't have to read 94 variables. You can just read like 3 variables to work for your use cases. Really reduce the data loading. And also you can do a predicate push down to actually filter by already predefined filter to get the best data to read to your local site. So this is the example of the lazy loading. So when we communicate with Parquet, first we communicate with the metadata, and metadata will give you what is the criteria for the data chunk in this in this Parquet data. And then we can redefine the filter and the column selection to actually just retrieve this data also in parallel to the client side of this small data chunk of inside the Parquet file. And this is the basic structure of the Parquet. So we have the partition level, and the partition level just the data set we expose as a stack. And using the stack, you can already kind of filter spatial temporal to get your interesting of the spatial temporal domain. And then you can apply, you can read the Parquet, single Parquet file metadata to get the information inside a single file, and just keep filtering that to get more predefined data. They only read the most predefined data into your local site. So this is how we organizing this data. I know this is not so much time for this presentation, so I don't want to keep everyone too long, but I prefer here is the GitHub repository that we are developing in this project, and there's a lot of way more detail inside here. For example, we have connected with OpenEO API, and then we use open source solution DocDB or PyArray to actually interact with this data. So you can always go to the tutorial in this. There's tons of tutorial, 1 hour, 2 hours tutorial to actually showcase how this data can be used and do for downstream research. So just feel free to get more detail, and I will happy to answer if you have any questions. So thank you.
Thank you very much. Thank you for keeping in time as well. I suggest we go for a break now. Thank you.